Welcome to the Passive House podcast, brought to you by Passive House Accelerator, a catalyst for zero carbon building. For news, inspiration, and connections from all flavours of Passive House, check out passivehouseaccelerator.com. Sign up to receive regular updates about events, get your questions answered, and contribute to the community dialogue. There's loads of free information for experienced professionals and people just starting out on their Passive House journey. We hope to see you at one of our weekly Passive House Accelerator live webinars. In the meantime, here's this week's Passive House podcast. Welcome back to the Passive House podcast. I'm Matthew Cutler-Welsh, coming to you from Tamaki Makaurau, Auckland in New Zealand.
And I'm Zack, coming to you from Seattle, Washington on the Salish Sea.
And as we're recording this, Zack, it's solstice.
It is. Happy solstice.
It's my shortest day, your longest day.
Yes, indeed. So you can have, you've rounded the bend.
Yeah. And it's a bit chilly overnight, and there's a couple of heat domes threatening life as normal in the US at the moment.
Yes, there are, and Seattle is fortunately being spared from all of that. It is absolutely gorgeous here.
Right. Yeah, I think it's hitting the East Coast more, isn't it?
Yes, it is. It's really intense over there. Yeah.
We've got a long but very interesting and quite important, I think, interview today, very informative. So I'm really keen to jump into that as soon as we can. So let's do a quick shout out to our sponsors.
Yes, absolutely. So a big thank you to NYSERDA, the New York State Energy Research and Development Authority. They're our stakeholder partner at Passive House Accelerator. Thanks to our founding sponsors, 475 High Performance Building Supply, Glavel, Ingui Architecture, Minotaur, Propel, Rockwell North America, Stocorp, and Zola Windows. And thanks to our champion sponsors, Bewizo, Icon Windows and Doors, Intelligent Membranes, pH Air Seal, and Source 2050.
Awesome. Now, as you mentioned at the top of this interview, Lisa White is a friend of the show, and she'll be familiar to many people who have listened to previous episodes. So I think we can probably put some links to other episodes of the podcast, but also articles and references from Lisa and the rest of the team at Phius. But we should probably just remind people of, we've got a few definitions. First of all, we jump into Revive, which is the Phius retrofit standard, and 2024 is an exciting year because that standard is being updated from the 2021 version to 2024. So you definitely go and check that out if you haven't already. There's some really good reading that we can reference. And as part of Revive, there's a thing called, what is it, Zack?
Adorb.
And you remember what it means?
I just had the tab open.
So that was a bit unfair. It's the annualized decarbonisation of retrofitted buildings cost.
Thank you.
So it's kind of how much do things cost to retrofit a building spread over the predicted life of that building. And it includes quite a few hard costs, but also there's some direct costs, but there's also some other sort of social costs in there. And we won't get into the formula here. We'll put links to that. But when we talk about ADORB in this interview, that's what is being referred to. So it's the annualized decarbonisation of retrofitted buildings cost. Did you want to add anything to that, Zack?
No, I don't think so. Let's dive in.
All right, let's dive in. This is Zack's conversation with Lisa White of Phius.
I'm excited to welcome Lisa White, Associate Director of Phius, to the Passive House podcast again. Lisa, welcome.
Thank you. Thanks for having me.
Yeah, absolutely. I'm so excited about this conversation. We have a lot of really great stuff to dive into. I think listeners will be very familiar with you and your work, but I just want to highlight for folks that Lisa is Associate Director of Phius, an incredibly important organization in this societal project to decarbonize buildings and make them more resilient to the impacts of climate change. She's also a key thought leader in the relationship between buildings and the clean energy transition. And Lisa, it was really fun to see you at the Humid Climate Conference in Austin just a couple of months ago, speaking with another key thought leader, Chris Nelder from the Clean Energy or from the Energy Transitions Show, a great podcast. So great to see you again.
Great to see you too.
Yeah. So I as I mentioned, I mean, we're going to dive into a couple of really important pieces of work that you've been involved in, including the Architect's Guide to Ultra Low Energy Buildings, Microgrids, and Direct Current that you authored with Walter last year, and then also I think we'll have a chance to dive into also the revision of Revive. Before we do that, we just heard from the Department of Energy on June 10th of 2024 here about their national definition of a zero emissions building. So I'm looking forward to hearing your reflections about this. And just to tee this up a bit, I mean, in some ways, this is really exciting. It outlines three core criteria for what a zero emissions building is. So it needs to, so just reading from the document, at a minimum, a building that achieves zero operational emissions from energy use meets the following criteria. 1, energy efficient. The building is among the most efficient. 2, free of on-site emissions from energy use. The building's direct greenhouse gas emissions from energy use equals 0. And 3, powered solely from clean energy. All the energy used by the building, both on-site and off-site, is from clean energy sources. So that all sounds great. And I think, could you reflect a little bit on how Phius measures up against those three?
Sure. Yeah, sure. So first off, when we learned this was coming out, we had to remind ourselves this is just a definition. This is not a certification program. This is kind of just a definition. So it's really the question of how did the Phius standards kind of align with this? So I think the definition is intentionally broad and vague and maybe a little bit left to be desired in terms of stringency. So first off, the kind of key point that it's trying to hit on is that the buildings are highly energy efficient. The criteria that they outlined there to what an efficient building is definitely leaving some, a little bit to be desired, some low-hanging fruit on the table in terms of efficiency, definitely relative to Phius. So any project that would achieve Phius certification or achieve Phius's levels of performance would absolutely meet the definition of highly energy efficient. Debatably, their highly energy efficient is kind of middle of the road energy efficient.
Right.
From our perspective. But, we're striving for quite a bit. So, but I think in general, it's good to set a boundary somewhere and kind of make that definition. And I think the definition is kind of creating that infrastructure to build, whether it be incentive programs or other things, into alignment. It's good to have kind of a common understanding of what it means. So I think in general, it's great that there's a definition out there, even if it's not exactly what we would have written at Phius, right? So good for them getting started. At least highly energy efficient is not just code. So at least they pushed beyond that. We'll take that as a win. The second part, the free from on-site emissions, this aligns with Phius 0, where we're basically don't allow for on-site combustion of fossil fuels. So that does align with our definition of 0 in our standard. And then the powered solely from clean energy is also pretty vague. And I assume it's thinking about a net concept like many do with net zero. And then they have like a handful of on-site and off-site options, which again aligns with our Phius 0 program. So Again, I think they're intentionally kind of broad and vague here and trying not to close the door on anything. I think overall this is the recipe. Whether each of the ingredients was, measured in the right quantity, I'm not sure. But I think it's roughly getting there. So it does align with Phius Zero. Phius Zero just gets you more efficiency, basically.
Right. Yeah, exactly. That recipe of be efficient, electrify everything, and power that with a clean electricity is, right in line with I think our broad understanding of what decarbonization means in buildings. And then there's this disappointment a little bit that the energy efficiency is pretty incremental as opposed to as kind of transformational that a passive building is. So what I think is interesting about this is how it relates to your work in this architect's guide. Because this is the architect's guide to ultra low energy buildings, microgrids, and direct current. And, in that guide, you found kind of the power of, envelope efficiency, in microgrids. So, I think we probably should start with what was the purpose of the guide? What was the context of creating the guide? And
Sure.
Then we can dive into some of the details.
Sure. So maybe I should start. It was funded by the AIA Upjohn Grant. So an opportunity came out in 2021, I think. And what we really were trying to look at is when looking at the total energy transition and electrification and all these different pieces, how big of an impact does the building enclosure actually play? Or how big of an impact does it actually have? So that's kind of where the study came about. We've always known it made a big impact on, the infrastructure required, not just for like getting to net zero, you can reduce your loads and use less PV to get to zero. That's obvious. But what if we're looking at something at a larger scale and trying to meet different goals, such as resilience or neighborhood decarbonization? How, like, the enclosure is one piece of that pie, right? Like how we meet those goals can be met with a variety of things. You can add more renewables, more energy storage, more smart infrastructure, and then the enclosure is part of that. So we wanted to really understand kind of how big of a difference the enclosure made versus those other factors. And that was the motivation behind the study. And so the report itself is a 2-part report. Part 1 is this kind of architect's guide, which introduces the concepts of decarbonization, load profiles, electrification, and all of these kind of things that go into thinking about the how and the why of the energy transition and how the decisions we're making at the building level are impacting the energy transition from a cost and infrastructure requirement perspective. So that's kind of really just kind of laying the fundamental groundwork for the concepts that are then applied numerically in the case study. So the case study broadly is saying, I want to find cost optimized packages that will meet different resilience and decarbonization goals for an existing neighborhood block. That's kind of it at the grandest scale. But because there's a lot of different steps to get there, we studied a lot of different things along the way as well at the building scale, up through the neighborhood scale.
So one of the things I was really loud and clear with the report was this communicating the agency that architects have to really make a big impact on decarbonization through the envelope. And in order to kind of lay the groundwork for that, sort of insight, you did a great job of kind of providing a 101 about the grid and the challenge of decarbonizing the grid, because we're talking about a big change, and there are so in understanding kind of the different roles of the different components of the grid and this transition, you talked about load modifiers, load disruptors, and load aligners, and then finally finally load flexibility, which is what I think really interesting around passive buildings. Could you talk a little bit about modifiers, disruptors, and aligners, and provide some quick examples?
Yeah. So maybe we talk about modifiers at first. So when we're thinking about a load profile, we're thinking about essentially power consumed in a building over time. So typically we're looking at like a daily cycle and looking at the power that needs to be provided that building to operate. So load modifier might be something like typical energy efficiency, reducing lighting use in a building. Maybe it takes that load profile and it brings it down just a little bit if you're reducing lighting, or maybe you're increasing the load a little bit. But it's not significantly changing the shape or magnitude of that profile. It's just
like an incremental code improvement too, right?
Exactly. Yep. So changing something that kind of like across the board or across the day might reduce the energy use needed by the building. A load disruptor is something that fundamentally changes the shape of this load profile. And that could be building electrification in terms of electrifying a heating load to a building that didn't already have heating electrified. If you think about a winter day in a building, if it's not using electricity for heat, the load profile might not be significantly different throughout the course of the day because it's plug loads, it's lighting, it's appliances, things like that. When you introduce heating, now you have this significant heat load introduced into the load profile, and it could be, depending on the building, it could impact that load by a factor of 5, 6, who knows, just because you have electrified or shifted the load from natural gas to heating. So now we've changed significantly what that load profile looks like. And then a load aligner is basically anything that brings a building load in alignment with clean energy supply, ideally. So this is maybe part of the bigger thought regarding how the energy transition can be accelerated, is really thinking about when our energy supply is available, our clean energy supply, and how our building loads can align with that. So an aligner might be something like a smart thermostat that can take a signal on when costs are high on the grid, which is generally a proxy for higher emissions. Maybe you have to set back the thermostat or use a little bit less for AC or heating, whatever it might be. So something that's bringing the supply, bringing the demand in line with the available supply.
Right. Because not only are we disrupting the load with electrification in this transition, but we're also moving from fossil energy to renewables, which also have which is a big disruption on the supply side.
Yeah, it's a very different. It's a big shift in terms of how the grid can operate. Currently, most of our resources are dispatchable, which means I need more of this, turn it up. And they're coming from central resources, generally central plants. Whereas as we integrate more renewables, we have more variable energy supply that is somewhat predictable, based on wind patterns, and we know when the sun shines, right? But we don't know exactly how much we're going to get on a given day. And we can't tell it to turn up or turn down, which fundamentally is just going to be a challenge with the whole energy transition. And the report doesn't get into EVs either, electric vehicle charging, but when you're charging vehicles at home or wherever, that's definitely a load disruptor. That's a significant need for power immediately. That could be as much as it could double your building load or more easily. So it's definitely disruption, but can also be an opportunity because the energy storage is a really good example of a load aligner, because you can store excess supply and then use it when the supply is lower and there's more demand. So aligning, even though the timing is not right, that battery is kind of the thing that aligns the supply with the demand.
Right. So the electric vehicles have the potential of being an aligner as well. Right.
Yep.
Right.
Yep.
Yeah. So how about load flexibility? Like, why is load flexibility important in this world, and how does passive building play into that?
Yeah, so load flexibility is kind of just like load alignment. The way I think about it is making the loads flexible so that when clean energy is available, you can align the building load with that. So typically where this is seen is the smart thermostats, like I was saying, heating, cooling loads. hot water heating loads, for example. There's a lot of potential there with heat pump water heaters or electric water heaters, like shifting like preheating a water heater or shifting, basically when the water heater turns to, crank up after it's emptied. The biggest loads in many buildings are the heating and cooling loads, the space conditioning loads. And with passive building, of course, we're driving those down. But what passive building also does is it introduces kind of like a thermos or a nice enclosure that allows you to shift the timing of the heating and cooling that's actually supplied to the space. So the active heating and cooling to almost whenever you want, because of that nice enclosure. If you think of like a really nice cooler, for example, you can put ice in it at one point and come back a day later and there's still ice in it, right? Or like a nice thermos with hot coffee. So it's less about, quick responses to changes in outdoor temperature because the building doesn't see that because of that nice enclosure. So passive buildings inherently have some ability to be flexible with the heating and cooling loads, which is typically one of the larger loads in the building. So if that can be a resource that can be kind of moved around, shifted or shedded, which so shifted would mean changing the timing of that load. So maybe you're heating a building in the morning and not again, in the middle of the day or whatever aligns with what resources are available. Or shedding might be, there's a really high peak on the grid, turn my thermostat off or turn my heating off for a couple hours. That really should not make any sort of difference to an interior temperature in a passive building, should have no impact on occupant comfort or any of that. And a lot of the studies that we've shown prove that through some like outage studies, which is more extreme, but just cutting off the heating, very minimal impact. So we have the ability to use that very large load as kind of a toggle and align with when energy is available, clean energy is available.
Right. So store a battery is like a classic aligner. So load flexibility is essentially like the building as a thermal battery.
Yeah. And for the heating and cooling loads, of course. Yep.
Right.
Yep.
Right.
Yep.
Awesome. So what is a microgrid, I guess, for folks who don't know, and why are they important? And let's start with there.
Yeah. Okay. So a microgrid, the definition is kind of broad, vague, but I'll go with it. There has to be energy supply, energy demand, energy storage, and then some sort of like central thing that controls all of those, right? It can like see into the available capacity or loads demands on that system. The why kind of comes into some of the challenges we were talking about with the energy transition, but also hits on a few we haven't talked about. So the microgrid has those components, but it's also at a smaller scale, if not obvious by the name, than our central grid. One key component is that it can island from the main grid, which means if the main grid goes down, it can disconnect and continue to operate on its own as an island from the main grid. It doesn't necessarily have to maintain 100% of all loads on the microgrid if it islands, but it can operate on its own. And that's kind of a fundamental piece of it as well. So the why kind of comes into the challenges of the energy transition. So the alignment that we were just talking about, this is a key piece of a microgrid, understanding the supply available, the loads, the energy storage, and having kind of the brain of the system be able to figure out how to align different loads or shed or shift different loads with what's available in energy storage and energy supply, etc. So that's kind of like the operational part of it. So the alignment is part of it, but a bigger part of it, I think, is thinking about the existing grid infrastructure that we have. I think it's getting fairly well known that it's aging quite a bit, and the energy transition is not just going to be a bunch of large-scale solar farms, large-scale wind farms that can just plug into the existing grid. It's just not going to work that way, and it's being shown as the interconnection queue. So this is the amount of projects that are ready to be funded, like renewable projects. It's years long, which means, sure, we can financially pencil out a solar farm. Someone will develop it, but it doesn't fit in with the existing network that we have.
Right.
And that's a huge challenge.
Like the existing,
huge.
It's basically a massive bottleneck.
Yes.
I mean, the grid is currently a massive bottleneck. Yeah.
Yep. And when it, most of the infrastructure was laid out, we didn't have the technology that we have today. So a lot of it is pretty old, 25, 30 years old. And if part of this energy transition is going to require significant upgrades to this system, this network. And because of that, what microgrids do is it brings the supply closer to the demand. So it's typically small scale storage, possibly small scale wind. Some have generators, which could be natural gas. It's not all just renewable microgrids, of course not. There's lots of microgrids within our Department of Defense because they have a lot of challenges if the grid goes down for even seconds in terms of data and national security and all of that. So they have microgrids that run on fossil fuels, right? So microgrids aren't just unique to renewable energy. I just think they're one part of what a solution can be in this energy transition. And the other part of it is with this aging grid infrastructure that just inherently leads to less grid stability, more outages, and more issues there. So resilience is becoming ever more important. So microgrids can provide that resilience with the islanding concepts. And then one more thing that I think is really important with microgrids is depending on how they're set up and the scale of them, they have the potential to provide energy independence to communities. So we've seen what it looks like if, I won't use examples, I guess, but if fuel sources are cut off from certain areas, how you realize how vulnerable we are to certain resources. If you're able to produce all of your own energy within a certain network, and it's owned by that community, energy independence, I think, just has a lot of potential to bring, or it can bring a lot of potential to different communities, not just lack of vulnerability to fuel prices, but more than that.
Yeah, absolutely. And I should take a moment to just encourage everyone to go to the Phius website, and we'll include a link in show notes to download the report. So there's for instance, there's a step-by-step kind of guide for how to approach designing a microgrid if you're as excited about these as I've become from reading the report. They're also with all the examples that you were just going through, Lisa, with load modifiers, disruptors, and aligners and stuff. They're really very elegantly crafted infographics, simple graphs to illustrate each of those points. So definitely encourage everybody to check those out.
If I can add I can add something there. If you're not a big reader, we did do 2 webinars on the report, which show all the graphics and talk through all the graphics. So you kind of get what you would read, but in a webinar instead. So those are linked on the same page as the report. So I can,
perfect. Yeah. So that's what a microgrid grid is and why it's important. So what did you find when you were running these? I guess first, could you describe the Wisconsin case study, and then what you discovered?
Absolutely. So I'll try to step all the way back. We picked looking at an existing neighborhood in Milwaukee, Wisconsin, which is climate zone 5A, similar to Chicago. It wasn't an actual neighborhood, but it was buildings that kind of exemplified what the neighborhood would be like. And we studied what it looked like to electrify those buildings. And so first step was electrify all of the buildings, give them all the same high performing equipment. And then the next step was to study how that varied in terms of load profiles from if we upgraded the enclosure to existing code, which now is the IECC 2021, or to Phius 2021, and how that impacted load profiles. So there's a little bit you can study just at that level. What are the carbon emissions of the building, pre-electrification, post-electrification, and then also so there's your typical building operational load day to day. We also studied critical loads. So if there were a main grid outage, what would the building load be if we wanted to maintain a survivable condition inside, which is a certain temperature range, a fridge, a couple of phone chargers, things like that. And then we also looked at flexible loads, which meant like looking a little bit at the load shifting and shedding based on grid emission signals. So that's kind of the setup. So we had to study at building level, what are the building loads with all these different variables. And then we studied at the building level in combination with different goals that could be achieved through renewable energy and energy storage. So the study honed in on just two options there. So we had battery energy storage and we had solar power as kind of the renewable supply. And the goals could be just, I want to operate this building at the lowest total cost. What should I do? So we went from that, smallest scale to, I want to make sure my building can sustain a critical load over a 5-day grid outage in the worst week of winter. What system do I need for that in terms of solar and storage? So, we went all across the map in terms of stringency, just so we could play around with different factors and see, again, like how big of an impact the enclosure had on these different cases. So like looking at a resilience case with a code enclosure, even at a single building level versus a Phius, how much more energy storage and solar power did that building need to maintain a habitable condition for the occupants during that outage versus if the enclosure was never touched. So we kind of started there at the building level and then aggregated all of that to look at kind of what does this look like on a grander scale, at a neighborhood scale, looking at similar goals. We did a lot of different simulations, looked at a lot of different variables, because we wanted to really see the gravity of the enclosure versus other things. Like, what if I change how long my analysis period is? What if I change electricity costs? What if I change the cost of PV, the cost of energy storage? Like, all of these things matter, right? If your goal is, let's say I want to decarbonize a neighborhood, you have all these different toggles to play with. You can add more supply, you can add more storage, you can make the buildings better, you can make the building loads more flexible. But how far do you go with all of those pieces was kind of what we were trying to understand. So by studying the various enclosure levels, it became like pretty abundantly clear that the enclosure was by far the thing dominating the size of the system required to meet that goal, whether it was decarbonization or resilience. It made more of an impact than any of the other factors that we studied. And that was kind of what we set out to look for and really understand, because it's kind of used as a proxy for looking at the greater energy transition, right? We just looked at 25 buildings, but who cares? Like, the concept is the same, right? And we did, I'll admit it was a little constrained because we just looked at solar and storage. But the sooner, you introduce all these different variables, it's kind of hard to draw conclusions, right? So we did look at a lot of different variables in terms of the analysis, and it was always a cost analysis, looking at the cost optimum result or system based on the goal in the building load that had to be met with that, or neighborhood load.
Right. And the case 18 was the case where you looked at what does it take to be 100% decarbonized. And the life cycle cost numbers are that one all electric existing enclosure neighborhood, so existing level of a performance neighborhood, could be 100% decarbonized for the same cost that you could decarbonize 6 Phius enclosure neighborhoods. So a 6x better result by doing a passive building, or doing passive buildings in the neighborhood. Right. And this is an extreme case because it goes all the way to 100% emissions reduction. But hey, that's what we're going for, right? And as we approach getting closer to that, I know we're nowhere near it at a grid scale right now, but that next percent emissions reduction is going to get harder and harder. And the solution is going to change as we approach 100%, even 50% emissions reduction or decarbonization. The solution is not always just going to be, okay, just add more solar, or add more storage, or add more wind, because there's other solutions that cost less that are actually going to achieve more,
right? And so that's kind of one of the big takeaways of this is not just did the enclosure have a huge impact, but also it had a bigger impact the further you were looking to decarbonize.
Right. And on page 47 of the report, there's this varying, you're take a look at the kind of the fact that there are these, exponential curves, essentially. So the closer you get to 100% decarbonization, you get a big upward curve in the cost of getting there. But when you compare the passive buildings with code buildings with existing buildings in 3 lines, that curve, yes, the passive building curve goes up at 100%, but it is so much lower than the numbers for the code buildings or the existing buildings. So well illustrated there.
Yeah, thank you. That really goes back to what we were talking about with alignment of supply and demand. So, it's maybe easiest to align the first 80% of the load with the energy supply. But when you're getting very peaky loads or buildings that have extreme spikes, you're getting these outliers that are really difficult to meet with just more supply, right? Because more supply isn't necessarily changing the timing of the supply, it's just more. So the reason that it's so different with the existing enclosure is because those loads are so spiky, and there's so many of the hours or the kilowatts that these existing building enclosure buildings would need that don't align with when the energy is available. Even when we're getting to lots and lots and lots and lots more renewable energy on the grid, lots of energy storage, you need like significantly more supply and storage to try to meet those weird outlier hours. So that leads right back into the load flexibility too. If we could shave off, I don't know, the top 20%, I don't know the number, but if we can shave off some of those peaks through load shifting, load shedding, that can bring that number down significantly.
Right.
And there are I don't remember the case numbers off the top of my head, but we did try to study that with flexible load cases where we looked at the typical load of the buildings and then shedding load during the highest emission hours. So we had to look at hourly emissions profiles and say, okay, the emissions are really high on the grid right now, shed my space conditioning load, and then kind of funneled that into the decarbonized case just to kind of see how big load flexibility could play a role in this as well. And it was significant, and it was a very rudimentary look at it, but I think conceptually it shows that there's a huge place for load flexibility in this.
And when we look at the kind of the implications for the larger grid, the big grids and the transition that we need to see. I mean, you already mentioned the bottleneck that the existing grid infrastructure represents and this long queue of clean energy projects that are going to be waiting for years to be able to come online. But another piece of this, if we have to overbuild, I mean, essentially it's, if we're not optimizing this transition and we have to overbuild a bunch of solar energy and wind energy, there's also the pushback from NIMBYism, we don't want to, there are sensitive natural areas that we want to avoid, creating the big solar farms in. I think that sometimes the fossil fuel industry folks and the people who are trying to slow down change create a lot of fear and misinformation about really the land area that the energy transition represents. But still, there are politics involved here. So if we can reduce the number of solar panels we need to deploy and wind turbines we need to deploy, it'll make the transition politically easier as well.
Absolutely,
which is so important.
Yeah, and let's not forget that it also takes energy to make these structures and systems, right. and so. Right. At a certain point, you have to invest a little bit of carbon to save a little bit, at least at this point in time. Like manufacturing is not clean. So it's a big, delicate balancing act. But I think we're putting way too many, resources or attention to the supply side, the supply side, and thinking that adding more solar and wind is going to solve it all. because that's just really fundamentally proving that that's just not, maybe it eventually could, but not in the time frames that we're looking at. We need like all hands on deck.
Yep.
Got to look at the supply side, got to look at the demand side, with kind of equivalent levels of attention.
Yeah, actually, going back to Chris Nelder, his most recent podcast episode is I'm forgetting the name of the gentleman that he interviewed from the UK, but was looking at demand side and acknowledging that we so often are so focused on the supply side when we're talking about this transition, but the demand side is so powerful, and this very kind of robust suite of studies in the UK found that energy demand could be cut in half with efficiency measures that really involve no hair shirts, no decrease in the energy services supplied. And a lot of that comes from electrification, and a lot of it because electrification is inherently energy efficient compared to fossil fuel energy. But a lot of it comes from things like enclosure improvements. So we need to trumpet the demand side more, and this report does a really great job and provides rigorous analysis and data to back up the claim, and it's a really important contribution.
Thank you. And if I may add something to what you just said about kind of cutting energy in half without making people wear sweaters all the time or whatever, double their socks. I think it's clear that efficiency already has kind of a little bit of that tendency in the average consumer. It's like, I have to cut back on something, or, you're taking away from me. I hope we can avoid that same mindset, or kind of, take on demand response or load flexibility. So when you're thinking about a utility controlling your thermostat, that like inherently kind of makes you uncomfortable. So I hope we can get out with the right foot in front with that whole concept, where we're not changing the outcomes in this building. So, you need XYZ, you need certain interior conditions, you need comfort, you need these pieces of equipment to be running, to provide whatever outcome. But if we can adjust the timing of it to help align that demand with supply without changing the outcome, I think that's really the picture. Because I'm already very worried about the consumer's point of view with load flexibility. It's like taking away freedom, and it shouldn't be. Right. So I already see that coming, and hope we can create a different narrative around that. That is
speaking about politics. Yeah.
Yeah, it's a challenge. It's definitely a challenge.
Yeah. And just another thing about that interview that I just mentioned too is that if the UK were to do that and bring it down and per capita energy use by this 50% number, that would be at or below the average global per capita energy use. Wow. So it also calls into question this idea that it's impossible for the rest of the world to have a good life, lifestyle. Because if we can all do it at or below the average energy use, and then we can decarbonize that energy use, then we can make this happen. So go ahead. No,
I was just going to say it's very technically possible. I think there's a lot of other barriers in the way. Yeah. Go.
Yeah. Yep. Yeah, totally. So I think you have this work really has this really important focus on resilience and carbon, and the other piece of work that you all at Phius have been involved in and moving forward also does that. A lot of things do that, I'm sure, but the one that I was hoping to talk about next also does that. And that's the revision to the revised standard. Can you describe the revised standard, like, it's for existing buildings. What was the problem that you're wanting to solve with the revision?
Sure.
And then what is it, how is it being solved?
Sure. Okay. So Revive 2021 exists. It is the existing retrofit standard for Phius. And it very much aligns with our new construction standard, which was rooted in looking at upgrading a building using passive measures to reduce total cost, which is cost of operation and also the cost of the things that go into the building. So like your mortgage, what the building costs over time. And that kind of equation just doesn't fit quite the same with retrofits. So we have a lot of challenges with, deep energy retrofits, decarbonization. But one of the big questions is like, how deep do you go and how do you justify how deep to go? And so that was one of the main things we were trying to solve. And then the other thing is thinking about the emissions impact and thinking about bringing carbon into the picture. The new construction standard does address that through source energy, as a proxy for carbon. But if we're thinking about existing buildings, any upgrades that we make to this building inherently has embodied carbon, right? Insulation, whatever, all the work, everything that goes into it, we're putting more carbon into that building. We need to make sure that over time, what we're putting in isn't going to result in more life cycle cost, including the cost of carbon, than if we didn't touch the building at all, right? So that was a really important concept that we wanted to embed in the standard, is just to make sure, we're checking our bases. We're not putting too much in certain elements that it's actually tipping the scale the other way. So with the revised standard, kind of the fundamental shift, actually there's a lot of shifts, but because it's existing buildings, there's this whole kind of auditing process just to start with, addressing any remaining defects, making sure it's a healthy building, making sure it's a place you should build that's not going to be underwater in 10 years or, in a flood, things like that. Really just looking at the building in a way we don't look at new construction, just because we're thinking about investing 100 years of life, if not more, into this building. So that's kind of one part of it that's very different than new construction, is this like upfront audit, of course, that you need with existing buildings. But one of the big places that it changed was determining how far to go with the passive measures. So it's still a passive building standard, but how far you go now in terms of insulation and air sealing improvements and window U values and things like that is based on resilience now. So we want to ensure that the package provided for this retrofit maintains survivable conditions for a certain period of time in the event of a main grid outage. So that is how we drew that line. And it's very different from before. It's not based on cost at all. In that element, the enclosure element's not based on cost at all. It's based on resilience. And we're looking at that from a kind of critical week in the summer and a critical week in the winter. I think we're looking at 5-day outages in both cases, but in both seasons. So we're not just focusing on heating or cooling or, things that help one or the other. The other big part, like I said, was focusing on or including carbon, like directly including carbon in the calculation. So this is included through our life cycle cost metric, which is called the ADORB cost, annual decarbonization of retrofitted building cost, I believe, ADORB. But it includes 5 key factors, 2 of which come directly from carbon. So the cost to operate the building, that's the same as new construction. But what's the cost of the carbon emissions associated with operating the building based on an hourly basis of carbon from the grid intensity that you're in? The cost of the upgrades to the building. So the more insulation, the air sealing, the better windows, whatever that is. The cost of the embodied carbon in those materials. So not just like, it cost me $100 for this, but how much embodied carbon was in that and what's the cost of that from like a societal scale of carbon. So I'm saying there's a cost of carbon. I know no one's paying for carbon right now, but we're putting a price tag on it in order to weigh it against other things. And then the last metric is actually pretty aligned, similar to what we just talked about in the other report, but it's the cost of the energy transition to support that building. So what is the increase in the peak load of that building because we electrified it? And we didn't talk about it much in the when we were just talking about the report, but the peak load of the building with the different enclosure levels was really in line or related to the infrastructure required to support the building. So what is the cost of the additional renewables or storage that you'd need to support that building for typical operation? That's kind of that last piece of the adored cost. And so in that life cycle cost metric, we want to make sure that the proposed retrofit's life cycle cost is lower than the building right now. And that's kind of it. The other really big shift is that the modeling tool can do parametric studies and identify kind of a range of packages that will meet both the resilience metrics as well as that lower adored cost. So it almost takes a building in and then gives you different recipes or packages of buildings that meet both of those metrics for the lowest kind of adored cost or life cycle costs. So there's different options and different packages that you could use to meet those goals. And that's not how the Phius standard works right now. You kind of design a building and make sure it stays in certain constraints with either the prescriptive checklist or the energy model. This is kind of approaching it from an outcome-based perspective and saying, what gets me that outcome? Which I guess that is similar to the new construction, which gives you performance metrics and says, meet that. We're just setting different kind of performance metrics from a life cycle cost and resilience perspective.
Right, exactly. And I think that's what, I'm super excited about this approach. And it does represent a real paradigm shift. You're moving from the focus on a specific air tightness number that you need to hit and specific energy performance numbers to the resilience performance in winter, a very cold week in the winter and a very hot week in the summer, making sure you can weather that passively or passively plus local renewable energy, right? And then the life cycle cost with carbon, integrated into it. It just makes so much sense for existing buildings. And I think, it seems that this approach also could be more scalable, potentially. Could you talk a little bit about that?
We hope that it's scalable. Sure. Just conceptually, I think it tracks with many people, but I think one of the biggest challenges is going to be making it a digestible format for consumers. It's taken a long time to get our new construction program there, and it is complex, some of the topics we're talking about. So how we go about packaging this and the accessibility to a builder or a typical user, maybe a homeowner, trying to determine, I want to upgrade my home. How do I see what would work for Phius Revive 2024? Like, we need to get that connection and figure out what that bridge is. I think the wide scale adoption helps because it should be a little more tailored, I guess, to the specific building and the specific case than our existing retrofit program. I don't know if it, in some cases, might be a little more stringent than our existing program. In some places, it might be a little more relaxed. We don't know. But the focus is different, right? So we're going to get a different... we know we're honing in on the outcomes, but the product and the path to get there is going to be a little bit different. So we're not exactly sure how all of it will pan out. But I think it definitely has a lot more potential than our existing program.
Right. And you're focused on laser focused on climate mitigation and climate adaptation. The climate mitigation piece is the life cycle cost that incorporates the cost of carbon. The climate adaptation piece is this resilience, the ability to be passively resilient when the stuff hits the fan with the grid,
which is happening more and more.
Right, exactly. Yeah. Well, thank you for sharing that outline, and I know that there are a number of tests, case studies ongoing now, and that we're still that you're moving toward finalizing this revision, and it'll be exciting to see that develop over the coming months.
Yep, it should, fingers crossed, come out next month, which will be July 2024.
Awesome. Yeah. Awesome. Okay, great.
Yep.
Well, thank you, Lisa. I've taken up a bunch of your time. I really appreciate you sharing this work and doing the work in the first place and sitting down with me to share it with everybody on the Passive House podcast. Really awesome.
Thank you, Zach, and thanks so much for inviting me. I love talking about this stuff, and to anyone that wants to listen. So appreciate it.
And that was Lisa White talking about a whole bunch of things, from microgrids through to the imminent release of Phius's new retrofit standard, Revive, and I definitely recommend going and checking that out. Diving into some of the definitions which are now available, and we'll put a link to where you can find those, because I think it's really useful for a whole bunch of reasons, not least of which really quantifying what it means to have a building that is survivable and will be survivable. Zach, is there anything that you wanted to mention straight off that interview?
Well, I mean, I'm eager to hear your impressions, but just riffing on what you just said, I think that one of the things that's so exciting about this revision of Revive is we often there's this debate in building decarbonization circles about how far should you go on a retrofit. Does it make, like, we know that there's often going to be a carbon burp from the retrofit work itself, the so-called embodied carbon of the materials that go in it and the construction process and stuff. Is it worth it to do that for the operational carbon savings that come later? So that's part of the debate. And then the other part of the debate that we passive house folks will bring up is, well, it's not just it's absolutely about climate mitigation and about carbon. It's also about climate adaptation and how can we make sure that the buildings we're in are going to protect us from climate extremes. And what is super great about the work on Revive is that it is specifically looking at both of those questions as central performance metrics, essentially, for whether and how far to go on a retrofit.
The main things that I got from listening to this was a reminder of that Passive House works, and it works because of the focus on the building envelope, and that realization of, well, I think the quantification, the evidence showing just how much impact working on the building enclosure has on overall performance, and that's something that is often missed. The other thing that's often missed is whenever we have a crisis or a energy supply issue, the focus is on supply. And we've had this just recently in our first cold snap of our current winter, when we were all told that we might have to conserve energy because our hydro lakes were a little bit low, the wind wasn't blowing, and then there was a lot of finger pointing talking about the previous government, their lack of investment, blah, blah, blah. And it was all about, we need more generation. There was hardly any until we kind of raised it. There was hardly any discussion about, well, what if we actually reduce demand? And that's the benefit of focusing on building enclosures, particularly of existing buildings. So I think really important. And you referenced the UK study, and we should also do a shout out to the energy transition show.
Yes,
one of your favourite podcasts, I think.
Indeed, yes. And I got to hang out with Chris Nilder in Austin too at the Human Climate Conference for the first time, which was great. And Chris, and I think I mentioned, but Chris and Lisa both presented back to back at the conference. It was really a powerful duo.
So check out episode 225, I think it was, of the Energy Transition Show with Professor Nick Eyre, which was about demand-side solutions from the UK. It seems that issue is relevant all over the world, because we've got the same thing here, and there's some great research coming out of Otago University in Dunedin showing just how much benefit doing deep retrofits to a passive house standard would be for the New Zealand electricity and energy grid. So it's very common, but it's common within our circles, I think, but we just need to keep talking about that and the value of retrofitting to reduce the demand side. And then Revive, really good reminder that this is happening. There's a lot of work going into it. I remember seeing the first drafts of the discussion documents, and now, as Lisa says, it's about to be released, scheduled for July this year, 2024, which is very exciting. And if I had to summarise Revive, I would say it just sounds like a really good tool for decision making to figure out how deep you should do a retrofit of any building. And that's really the challenge, is to figure out from a carbon point of view, but also from an energy use and ongoing operational cost perspective, what's the right amount of retrofit to do? And that's the value of tools like Revive. I think it's interesting that Lisa pointed out that one of the big differences is that you've got to do an initial audit or initial survey of the building, and that is a challenge because it's easy starting with a blank sheet of paper and drawing a design for a new home. But when you've got a building there, you've got to kind of figure out what exactly is there first, and so there is that extra little step, but it's well worth it to help decide. And then what the Revive standard does is provide a framework for allowing someone to make a decision as to what the best outcome, and with that underlying goal of the proposed building having less embodied carbon, or having less carbon in total than the existing, which I think having that as a fundamental kind of principle of Revive is really, really useful. So I'm really excited to see where that goes. Lisa did talk about the scalability a little bit. I think that is a challenge, and I think doing that step is part of that challenge, and figuring out how we encourage people to make that investment in planning up front and figuring out in detail what is there before just jumping in and starting to design their fancy new bathroom and kitchen and all the fun stuff. I don't know. I think that's a marketing issue as much as anything else, of how we get that out to more people, to really inspire people to use this as a decision-making tool.
Yeah, I think, I just imagine kind of what the future could hold once we see this standard being applied more and more. It would be great, for example, to see some, basic step-by-step guidance to emerge from this, because I imagine that there will be some very common kind of rules of thumb. Maybe they're going to be climate specific rules of thumb emerging from this. And then also, in addition to the marketing piece, I think that there's the potential in the future for something like this to be really helpful to policymakers who are trying to figure out what is the smart way to deal with the problem of existing buildings. And those policymakers are going to be thinking from a kind of societal cost perspective, which is similar is what Adorb is attempting to do with cost of carbon, but and cost of energy and all sorts of different things included in that calculation. So
I think there's also
really fun to watch.
I think there's also a lot of scope for AI in the retrofit space, and for things like some automation. We've got some pretty impressive technology for computers that can interpret an image, and I see there lots of potential for some automation to be done around looking at existing building stock, and from estimates at least to be done to figure out that looks like this type of building with this type of enclosure material. Therefore, this is the most likely strategy for retrofitting that, and that makes scalability a lot more achievable. They're still going to have to be checking the details on individual, but it allows people to just kind of do things en masse at a sort of base level. So that'll take people much smarter than me to figure out, but I'm sure there's a solution there that uses computer technology, not just individuals going around with a tape measure and measuring up existing buildings, because we need to move faster than that. Awesome. We'll put some links. There's lots of information there, but definitely check out the Phius Revive 2024, and we'll also put some links to the Energy Transition Show and anything else that we find useful on that one. Taking a bit of a break at the accelerator at the moment, Zack?
On the live programs, yes. So we're not the Passive House Accelerator Live. Our Wednesday Zoom events will resume in September. So stay tuned for more information about the exciting season we have planned for you all. In the meantime, we'll be releasing a new episode of Passive House Podcast on Wednesdays, and upcoming for the summer. For those of us in the Northern Hemisphere, we're going to be focused on a series of conversations around cooling strategies for passive buildings, and the latest and greatest around that. So,
very good.
Lots to look forward to.
All right. Well, thank you. So we'll be back again next week on the Passive House Podcast. Thanks for listening.